Good evening, everyone. My name is Brandon Walker, and I'm excited to dive deep into a topic that is fundamental to modern software, TimSort. So, for a lot of us, sorting is just a library we call perhaps developing software, but the algorithm behind it is a masterpiece of engineering. The cool thing about TimSort is that it's the invisible hero powering Python, Java, Rust, and other programming languages. If you ever built an app that handles any kind of list or array, you've probably used the algorithm before. It's the industry standard and for a good reason. Over the next few minutes, we've got 6 clear goals. First, we need to grasp the underlying principles, why it was necessary to build a new kind of sort. Second, we'll talk through the step-by-step mechanics. I want us to see exactly how a computer handles this under the hood. Third, we'll talk about why it's the dominant sort used today. Fourth, we'll break down its hybrid nature, which is the core of its genius. This is how it flawlessly blends merge sort and insertion sort. Fifth, we'll define some key terms like run, galloping mode, and memory optimizations. These are keys to how it optimizes the pre-existing programs and sorting procedures that already existed before it. Finally, I've tried to make sure we visualize the algorithms clearly so this sticks long after the lecture. Alright, let's jump in and explore the history and the beginning of TimSort. What is TimSort? The story starts with a guy named Tim Peters back in 2002. It wasn't a huge academic committee that designed this or any corporation. It was just a 28-year-old guy, a Python developer, that was engineering a solution to a problem. He built it specifically for the Python language, which was growing rapidly at the time and needed an efficient general-purpose sorting function. What's phenomenal is how quickly it became the industry standard. It's the default sort in Python, but also in major production environments like Java's array.sort, or even in Rust and Google Chrome, such as like Android applications, use this same sorting algorithm. It's everywhere because it's the best general purpose option that we have available. The secret is the hybrid nature. Tim Peters recognized that the pure algorithms have weaknesses. If a list is tiny, merge sort is not optimized for small lists. If a list is really large and almost sorted, quick sort might have problems doing it efficiently. So TimSort combined the best of both, and it uses the speed and low overhead of insertion sort and the small data portions and stability of merge sort for the large structural organization and real-world applications. This is what makes it an intelligent system that chooses the best operation for the data at hand, which is exactly why it's so fast with real-world applications. Before we get too deep into the mechanics, we need to learn a few terms. These are the vocabulary lists basically for TimSort. First up is run. A run is a sequence of elements that are already sorted that could be ascending or descending. When TimSort looks at data, it's not looking at the individual numbers, it's looking at these already made runs. So if you have, like my example on the screen is 1, 2, 3, 4, 6, 7, 5. The second example on the screen, 1, 2, 3, 4, 6, 7, 5. The first run is 1, 2, 3, 4, and the next run would be 6, 7. That has 2 runs. Finding and using the existing order is the core idea of this mechanism. It's finding runs that already exist and organizing them based on this. The next term is min run. This is a parameter. It looks kind of like a variable. It's calculated based on the total list size. It's usually between 32 and 64. It sets the minimum length for any run that will participate in the major merge phase. We will find a run shorter than minrun. We will extend it using the insertion sort. So if you find a run like we found a run of 2, the run of 6, 7 is just 2. So we would actually keep gathering more and more parameters until we meet the requirement set by minrun. So minrun is just the minimum run requirement. Then we will move on to distinguish between merging and sorting and define what that means. Merging is the tactical operation. It combines two already sorted runs into one larger sorted run. Sorting is the overall approach. It's the hybrid process of insertion sort and merge sort, combining them into the final output. So we merge our runs, and the output we are sorting. That's what those two terms mean. Next is galloping mode. This is an optimization feature used during merging. If the algorithm sees that one of the two runs is consistently winning comparisons 7 times in a row, it will flag itself to turn on galloping mode. So instead of checking one by one, because it's already checked 7 in a row that were already sorted, so it turned on galloping mode, and now it's going to start rapidly skipping ahead to see if it can save time by skipping these checks and assuming that it's just going to keep giving you runs. This saves a lot of time whenever you have pre-sorted data. It gives you a huge speed boost if you have pre-sorted data. So the next term is real-world data. This is just to clarify that we're talking about the messy, complex, and partially sorted data that you will find in real-world situations like production fields and corporate data centers. Such as like fulfillment lists, which are rarely random. They're not random. They often have small bits of already sorted information. So TenSort is going to exploit that pre-existing order in the data. Next is comparison. This is the fundamental lowest level operation where two elements are checked. You're just comparing two elements. And for TenSort, we're comparing the values, like the lowest value is compared. The entire philosophy is to minimize the number of comparisons that take place, because to sort the two lists, you're comparing the lowest value because you're sorting it based on its value. You want to have to check the values the least amount of time as possible, because that's saving you processing time. So now that we have the terms, let's explore why Tim Peters was motivated to build it. Motivation. The motivation was simple. Old algorithms could not reliably handle real-world data dynamically. We couldn't rely on just one method to work all the time. Quicksort is usually fast, but it's unstable, which means items, if you give it multiple data points with the same value, you might lose the original order that you received those in, which is valuable information. The worst case scenario is also not optimal for quicksort in every situation. If you get that rare type of input, your application could have very slow processing speeds if you only use quicksort. It's not very manageable. Merge sort is stable and guarantees a specific worst case scenario, but it's very inefficient for tiny pieces of data. It checks everything individually. So trying to merge two arrays of 8 items is just slow. compared to running a simple insertion sort on those 16 items. So the solution to that problem would be TempSort. It's the smarter algorithm that detects small arrays and uses insertion sort. It detects structures and logic that already exist in the data and uses the appropriate sorting method for the fastest speeds. It also has the option to turn on galloping mode to adapt to runs within the merging process. It's an automatically adjusting algorithm that always uses the right tool for the job. Adaptability is a key part of this method. Adaptive merging is the secret. It means that TempSort doesn't just blindly merge runs in the order they appear, it strategically manipulates the merging order to keep the run sizes balanced. The whole idea is to prevent huge one-sided merges, which are inefficient. This would be merging like a run of 1,000 items with a run of 5. That would waste time and cause performance imbalances. By enforcing a strict rule on the size of top runs on the stack, TempSort will keep merges efficient and symmetrical. Again, the idea comes from combining those two great algorithms. Insertion sort is the macro manager it will use to deal with the small runs up to the min run length. Adaptive merge sort is the macro management tool. It organizes and combines the large sorted runs into the final list. The dual approach is used to leverage the strengths of both algorithms exactly when they're needed. So this is what makes TempSort the answer for real-world sorting, because real-world data, you're going to need the different tool at the different time, and it accounts for that. A huge benefit of this design is additionally its careful use of memory. Memory optimizations. So when you're dealing with large data sets, the memory optimizations matter just as much as the time complexity. Standard merge sort can be a memory hog because it often requires large temporary arrays. TempSort is much smarter. It only uses a temporary buffer for the smaller of the two runs being merged. So if you buffer the smaller run, you can efficiently compare its elements against the elements of the larger run, and you can compare the results directly back to the final sorted list. This reduces the memory overhead. There's another benefit to this here, that TempSort is a stable sort algorithm. If two objects have the same key or value, TempSort will retain the original order. This is non-negotiable for many use cases like managing customer records or transaction logs where the original input order is really necessary to preserve the context. We can also compare its performance against the algorithms it replaced. TempSort over QuickSort. The comparison with QuickSort is all about reliability and stability. First, stability. QuickSort is inherently unstable, unlike TempSort, who relies on its merge sort strategy to remain stable. This ensures that when values are input equally, it will preserve the order in which they were input. This is referred to as stability, and it preserves the context of the data that's input, which immediately makes TempSort the better choice. Second, the time complexity guarantee. This is arguably the biggest reason. QuickSort has the infamous worst case, big O to the n second power complexity. If a hacker or even a random piece of bad input triggers that case, your system slows down exponentially. Since Tim sort's large-scale merging is bound by merge sort, its worst-case complexity is guaranteed big O n log n. You know exactly the maximum amount of time it will ever take, no matter how maliciously designed or unlucky the input data is. This reliability is why it wins in production environments. The difference between n squared worst case and n log n worst case for a list of a million items can be the difference of a few minutes or multiple days of processing. This is a huge performance difference. Okay, Tim sort versus its other parent, merge sort. Tim sort is merge sort evolved. It has two huge advantages. So, a superior best case performance. Pure merge sort always does work, even on a perfectly sorted array. A completely sorted input, it will still work on the input. It still divides it, it still merges it, and it results in a big O n log n runtime. Timsort, however, detects the perfect order instantly. It recognizes the whole list as one massive run and finishes the sort in big O of n time. If you are often sorting already sorted or near sorted data, Timsort orders the run much faster. Okay, so it handles pre-sorted data much better. Next, efficiency on small runs. This is the insertion sort piece. Merge sort is slow on small arrays because of the overhead. Tim sort uses insertion sort up to the min run size, which is far more efficient. It leverages the fact that insertion sort is truly the fastest algorithm for arrays smaller than 32 to 64 elements. Next, galloping mode we will expand on in the next slide, but it provides adaptability. Pure merge sort has no way to skip over long sequences of sorted data. Timsort does, making the merging process dramatically faster when one run is substantially smaller or larger than the other. Alright, galloping mode. Galloping mode is the genius optimization that makes Timsort so fast in the real world. It's a dynamic performance boost. So the activation. It activates whenever the algorithm observes a pattern whenever 7 consecutive elements are taken from the exact same run during the standard merge. That streak tells the algorithm that there's a long sorted sequence here and that comparing them one by one is wasting time. So instead of continuing the slow comparison, the algorithm switches to a predictive search. It stops looking for the next element and starts looking for the end of the streak instead. It uses exponential search to quickly find a wide range where the element from the losing run must be inserted. Then it follows with a precise binary search within that small range to find the exact insertion point. This drastically cuts the number of comparisons. If you have a particular run with 10,000 elements and a second run with 10 elements, you don't want to compare thousands and thousands of times unnecessarily. Galloping mode finds where the block of 10,000 belongs almost instantly. It gives Timsort its name. It speeds up the merge dramatically. Alright, so let's start one by one, step by step, um, going through the process of how it logically, mechanically sorts data. Step 1. Calculate min run. Step 1 is foundational. Calculating min run is required. We need to determine the optimal minimum length for all runs to maintain efficiency. The min run is going to be between 32 and 64. It's calculated based on the input size, n, and it's determined so that n can be efficiently divided by the run size. It's also considered in making the subsequent merges symmetrical. It should typically be between 32 and 64, and min run is the minimum length a run must be before it begins to get merged. This minimum size is used to guarantee that the small arrays are handled by the best method possible, which leads us to step 2. Step 2. Identify natural runs. The algorithm scans the input array to find existing order. It's looking for runs that have already occurred naturally in the data. It's looking for the input that already has logical nature. It's pretty smart about it in that if it finds a descending run, it will immediately reverse it in place to turn it into an ascending run. This maximizes the length of the sorted segments with minimal work. But all we're doing in this step is just detection and addressing, basically. We're identifying the starting runs. If a run is shorter than the min run we calculated as step 1, we do nothing, but we mark it. In the next step, we're going to use insertion sort. Step 3. Min run and insertion sorts. Step 3 is the application of insertion sort. This ensures every run meets that minimum size requirement that we set with min run. So if a natural run is too short, let's say it has 15 elements, and we have min run set to 32, we would extend the run by grabbing elements again and again until it hits 32. This extends the run and is then sorted using a direct insertion sort. So we're extending it and sorting it. This is the hybrid part in action. Insertion sort is used to create these perfectly sorted, small-sized runs that are efficient to handle. Once the step is complete, every single run in the array is sorted and at least min run long, so 32 to 64. We are now ready to start merging in the next step. Step 4. Push runs onto the merge stack. Step 4, we're going to push the runs onto the merge stack. We take the fully sorted runs that are compliant with min run, and we push them onto the last in, first out stack. This stack manages the merging process. You could think of this stack as the merging queue. It holds the reference to where each sorted run starts and ends in the main array. This stack is what allows us to keep track of the runs and, critically, to enforce the balance merge rules. After pushing a run, the algorithm immediately enters a loop to perform the crucial merge check, which is step 5. Step 5, merge check. This is where the adaptive part of adaptive merging really shines. The goal is to maintain balance among run sizes on the stack. The algorithm looks at the top 3 runs on the stack, referred to as A, B, and C. It enforces strict geometric progression rules to prevent those lopsided merges. The rules are length C must be greater than A plus B, and length B must be greater than A. If these rules are broken, it forces a merge immediately, typically merging the two smallest runs on the stack until the conditions are restored. The constant check and enforcement means the algorithm is always perfectly um, balanced. It never gets bogged down in an unbalanced merge that could slow down the process. Once conditions are satisfied, we proceed to the actual standard merging. Step 6. The standard merge. This is the classic merge sort operation where two runs are combined into one sorted run. We copy the smaller of the two runs into a temporary buffer to enable that efficient in-place merging with the larger run. The algorithm then compares the first elements of both runs and places the smaller one into the final merged array. This is the step where you may trigger galloping mode. If the algorithm pulls 7 or more elements consecutively from the same row, it realizes that this isn't balanced. It stops the standard merge operations and hands the control to step 7, galloping mode. Step 7, galloping mode. This is the performance optimization we already love. It's activated by the streak of 7 consecutive wins from one run. Instead of the slow element by element comparison, we would then switch to search mode. We would use an exponential search to quickly find a wide range in the winning run where the next element from the losing run belongs. Once that general area is located, we use a rapid binary search to find the exact insertion point. This makes a huge difference, particularly when one run is much longer than the other. It essentially block copies large sections of data, drastically cutting down on the required comparisons. It's dynamic and intelligent, and it makes the sorting algorithm adaptive and fast. So overall, galloping mode, instead of comparing element by element, the algorithm begins to perform an exponential search to find the range of the next cut, and once it finds the range, it does a binary search to find the exact insertion point within that range. Step 8. The final cleanup. By this stage, the entire original list has been processed and merged into fewer, larger, sorted runs on the stack. The only thing left is to finish the job. The final step is to merge the remaining runs on the stack until we are left with a single completely sorted array. We start at the bottom of the stack, merging the two smallest remaining runs until only one fully sorted array remains. The result should be a stable, optimized, and guaranteed performance sorted list. The performance should be guaranteed at big O n log n. To wrap up, we should confirm the performance guarantee. We'll go into time complexities in the next slide to learn more about the performance guarantees. Time complexities. We use big O notation as our formal benchmark for how an algorithm scales with the input size. The input size is referred to as n. Time complexity for TimSort is pretty good. In best case, you have big O of n. If the array list is already sorted, It will just scan and finish. Best case scenario. Worst case scenario would be big O of n log of n, which is the guaranteed performance ceiling, um, which would also be our average case. The guaranteed big O n log of n, worst case, is the most critical feature. It ensures that your code is reliable. It guarantees a performance minimum. So you'll see best case, worst case, and average case performances listed for different algorithms, but um, these are your guarantees for the performance. Big O is the formal benchmark notation for how an algorithm scales. N is the input size. O n log n is a great speed for comparison-based sort, and it's why TimSort is so fast. So what did we cover? We learned about Tim Peters' motivation and how this algorithm became the standard for Python, Java, Rust, and even more programming languages. We explored the hybrid nature and the incredible efficiency of adaptive merging. We defined many key terms like run, min run, galloping mode, and stability. And finally, we walked through the 8 meticulous steps the algorithm takes to achieve its speed. I would also like to acknowledge the references and sources used, especially the fantastic resource from Geeks for Geeks, Karupa, and Liang's textbook. Geeks for Geeks provided really good technical know-how and knowledge regarding the technical aspects of how the processing of the algorithm works. Karupa, however, made a very easy to digest entry guide to begin learning about TimSort and how it works. Um, the textbook gave a lot of background knowledge and was especially useful when learning about time complexities and the specifics of Big O notation. I would be happy to take any questions you have about the merging rules or specific implementation details at my student email, and I hope you enjoyed my presentation and perhaps you enjoyed learning about TimSort and have a wonderful day.